Hello there. Let's do some applications of Faraday law. So there's a concept called self-inductance, and it can be for any circuit. You can say what's a self-inductance. So it's, usually we say self-inductance of kind of a solenoid, but solenoid has to be part of the circuit. So it's a self-inductance of this entire circuit is the better way to say it. But whatever formula we're gonna get is we're gonna just identify is mostly is coming from this part. Okay, so what's a self-inductance? Well, if you let's look at just an arbitrary circuit here, some circuit here, and I'm just gonna ignore everything else that's in the circuit. Just say it's some kind of loop, and the current can flow through this loop. So this is some kind of metal, and so this is current, but current depends on time. So if you look at magnetic field, there will be magnetic field going around. If you use the right hand rule, you're going around like this and going around like this. Like this. So if I look at this loop, and this loop is loop in space, this loop in space, and say I go along in the same direction the current, so this is my dl, and if I do E dot dl, then by the Faraday law, you expect this to be minus d dt of magnetic flux of this that going through that area, right? Phi b, and phi b is just magnetic flux, b dot n hat dA. So in here you can see that this from the loop, I'm going around the loop. The dl is in this direction, so using the right hand rule, the n hat is in that direction, and n hat is not changing. So you put it in there, it's going to be minus d dt, and this element is not changing. So this just would be dB n hat dA. So this will just be like that, and b dot n hat is in the same direction, right? So this will just be equal to all the b's in the same direction on that flat surface. So it just becomes a b, and so this just becomes minus dB dt into dA. And over here you can see that in this particular example, this dB dt will be different in different area, right? So I can't take this out of integral. So it's got stuck. I got this. The way you do the area integral is you divide into small areas, and over here n hat dA. So dB dt over here is different than over here, so on and so forth. So it can't come out of the integral. So this is the integral I have to do. Okay. So this is the minus EMF induced from this negative sign that will give you EMF. So that's what this is, minus EMF. So this is in addition to you can see this current that's going around has to be consistent with all of this induced EMF, right? So over here is the same kind of thing. This current that's gone there, so it has to be induced EMF, and the current has to be consistent. So when we look at this, this will be B itself, not ddt, but B itself will be proportional to the current. So when you look at B, where the current is going is, it's going to be proportional to current. And so if I look at this EMF, just take a minus sign off, EMF induced is going to be dB dt dA, but this is proportional to the current, so this should be proportional to the current. And so we can write this as some kind of circuit has some property that depends on the area and length and other geometry, how it's oriented. So the orientation comes from n hat. So this property, just purely geometric property, we can just lump them together and call self-inductance. So if I make it equal, and usually written capital L times I, and L is called self-inductance. So this is the definition of self-inductance. It's going to happen in every circuit, and this circuit is no different. So we're going to, you try to apply it to this problem and then see what formula you get. Okay? So basically what we are trying to do is, if I can actually work it out, if I can work out this formula and then compare with this, I would be able to read L. So there are not that many examples where you can really work out this integral. And so this is one of those cases you can work out the integral reasonably well, although it depends on all ignoring some of the things. So try to do it. Another example is an example like this. Maybe just for a circle, you can work it out also, that L for this integral. Okay, I'm going to leave that as an exercise, but we're going to just do this stuff over here. So I'm going to pause it and clean it up and then come back and try to solve this problem. Okay, so let's do this problem. I just want to maybe advertise a little bit before I solve the problem. You can go to this website. There's a whole chapter on inductance, self-inductance, mutual inductance, and things like that. You can get much more detail. If you like my channel, this video channel, you can subscribe to this channel. You can hit like button and things like that. Tell your friends. All right, let's get to it. So over here, as the current comes in and I use right hand rule, I'm going to get B field mostly concentrated here, right? They're not going to cross it, hard to draw. And this B fields, we're going to return like that, right? So this all and this B field might return like that over here, and this might return over here like that. So as the area of the integration, we are trying to do B dot n hat dA and ddt. We're trying to write something like this for here. Actually, just this. Just try to do this flux first. At t equal to 0, is 0, but at t not equal to 0, so t not equal to 0, there will be some I that depends on the t. So then it will have a ddt. But let's focus on just concentrate on doing this, okay? So I think I just realized what in the last video there's correction, a little earlier video correction. So EMF, I wrote down Li, but actually it's this L di dt. Okay, this is the correction. Because ddt I just forgot about when I was writing that down in my head. All right, so I have a b dot n hat dA, and this would be equal to EMF induced, and that I'm trying to write L di dt. All right, so if I can do this integral and then I compare with that, and you can get L, right? Okay, so let's see what area, surface area we are doing. Okay, subsurface area. So surface area here. So the loop is this whole thing, and then I come back. So this is the DL over here, and over here that's the DL. So DL is all over the place. So this is equal to minus E dot DL. So I can go all around and I got DL. So for instance, if I go a bit from here to here, that's the DL over here. And if this is voltage was 0 and this point was voltage was V0, then I'll pick up a voltage, right? So it's going to be minus V naught over there. So if I go all the way around, A, B, C, D, back to A, then the area would be, say this was completely flat, and then some area here, some area here, some area here, some area here, some area here. So those are the areas. So those will be the areas I need to do this integral over. So I'm going to assume, so to do this, I'm going to assume that this part, integral b dot dA, b dot n hat dA, is almost 0 compared to what will happen, or much less than over this B to C. So rest is much less than b dot n hat dA inside this B to C, inside solenoid. So I'm gonna assume that. So we can ignore this even if you don't know what it is and how to do it. Just gonna ignore it. Okay. You can ignore it because if there are infinite number of loops, this area will be infinitely large compared to this. If there's many loops, and also mostly the magnetic field is completely much higher density here than out here. You might say, oh, this has more area. No, density is higher and the area is also higher here. Okay, so both this is and this is less compared to this guy's inside here. Okay, once I've assumed that, then B is only in the B to C area. What do I get? Right hand rule, n hat is pointed that way, and the B is also pointed that way. So that just need b dot n hat, that's just equal to mu naught n, but this time I at that time t. So that's, I got to carry the time t. So this is a time dependent, so I get a ddt mu naught n it dA. Okay, these are in over here is the same over all the area, so it's, this can come out, and so this is mu naught n di dt, and this area A, we have how many loops there are, and times pi r squared. So this area A is number of loops times pi r squared for each loop, area of each loop. So how many loops there are? N turns per unit length, and then there are L length. So this will be N times L. And so I've got all the factors here. So this is mu naught n with n is n square. There's a L r square, and then there's a pi, and then di dt. So now compare with that. So this would be my answer. So this L is the length, and this L is the inductance. So I need to change one of them just to be. So let's call this that way. So this self-inductance equal to this thing over here, pi mu naught n square L r square. So that's the answer. Okay, this is one of the very few things you can actually do it. There is another one that you can do, and let me ask you to go ahead and try to do it. I'm going to get another clean slate. Okay, so the extension, and a new project I can give you is say you have some kind of ring, and on that ring, so this maybe non-conductor, a box like that. So you wound, so it's called toroid. You wind this. Okay, so you wind it, and then you turn the current at t equal to 0 to figure out. So figure out what the self-inductance of this loop will be. Find self-inductance. So you will need to figure out. So take one of these loops. So let's, from here to here is A, and from here to that, this is circle, and this is this circle also. So these are same. So you have well-defined distance involved. So this is coming to A, and from where here is B. So you need to figure out what's the magnetic magnetic field is going to be, say, some arbitrary point. So this is dA. So what's the magnetic field is going to be like, and what's the n hat will be like. So as you have a time current comes in at time t, what's going to be, so integration. So you'll see that the magnetic field will have the same value. If this is a radius r, so then this will be a function of r only. Okay, and so you should use the ring as an integration. So this is a little bit hard problem, so it's for people who are a little bit more advanced. So first, finding this, you can use Ampere's law. Use Ampere's law to find this. So once you know what the formula for B looks like, as at a distance of r, is a very distance of r, then you should be able to get the answer. So it's you should be able to do this integral that we speak about. So you do b dot n hat dA, and that will be all these areas inside, and d dt, and that make that equal to L di dt. And from there you can, if you do this integral, you should be able to get that what the L is. You should read up from here. So this will become something times di dt. Okay, maybe you can try this problem with your friends, and I think this may be also done over here. It's called toroid, and it's a good example to practice for if you're a little bit advanced in this subject. But if you're not advanced and you're still learning basics, maybe you can just look at this as a curiosity. Okay, so take care. Bye.